Thanks for the introduction. I also like to thank Victor for having me here, as well as the organizers, Michael, Ian Spielman, and Jairo, as well as Michael first. So my name is Edbert C, not Z, which means you in Germany. It's okay. So I am a graduate student in GEDIK group at MIT. So what we do in the lab is basically we use ultrafast experiments. And for my case, I use ultrafast transient absorption spectroscopy as well as time-resolved RPES in order to study solids. And the particular solids that I'm studying right now is a monolayer alphagenized, which is an interesting semiconductor which I will explain shortly. So the title of my talk is Floquet states and Bloch-Siegert shift in solids. So I'm going to show you that Floquet states can actually be used. Not only is very interesting phenomena, but can be used to tune the energy levels in material system for applications too. So the kind of material that we're dealing with is this. Yeah. So the material that we are dealing with is this thin semiconductors, which basically our job is to shine light on the material and look what happens when it changes. All right, so this material called the monolayer transition metal like alphagenized is a family of semiconductors. And one example that I use is the tungsten disulfide. So it's basically, it can be grown on top of a substrate, glass substrate, in this case is sapphire. And this material consists of the tungsten atomic layers, which is sandwiched between two sulfur layers. And this material is very interesting because, like graphene, it has the Valley degree of freedom. But unlike graphene, this material can be tuned optically to access the two values, the K and K prime values. So in this talk, I'm going to introduce this material first. And secondly, I will discuss about the Floquet states and how we can use these Floquet states for split the values. And then discuss about the proposal about the Floquet topological insulators, as well as, if we have enough time, we can look at some results on the high harmonics RPES on the TMDs. So perhaps one of the biggest thrusts in the development of 2D materials is the fact that, or an idea that integrated circuits can be made entirely by two-dimensional materials. So as you can see in here, in 1947, the first transistors invented in Bell Labs was about the size of the palm of a hand. It's big. And now by 2012, Intel can already produce a transistor as small as 22 nanometers. But despite the drastic change in size, these transistors are actually made of the similar components. First, they must have a metal, insulator, and semiconductors. And in the semiconductor components, nowadays we already have like 30 atoms wide. And not only that, TSMC in Taiwan, which is like one of the biggest global provider for semiconductors, for chips, said that, okay, the first quarter in 2017, we'll have 10 nanometers junction, and then 3 nanometers around 2022. So this means like basically 3 nanometers is like three times thicker than the monolayer semiconductors. That means eventually the chips will go into the regime of like very thin material. So one way of there is some thing about this thing is that this material, the transistor, if we go smaller and smaller, then it will face a challenge such as like quantum tunneling or source to drain leakage. So it will be a problem, which is can be costly or basically reaching the fundamental limits. So one way to pack more transistors in a chip is to stack layers of mini transistors. And in order to do that, we need to find layers of mini metals, insulators, semiconductors. And we know a layered metal, which is graphene, and insulator, which has a gap of 6 eV, which is boron nitride, which can also be made layer. And unlike graphene, which is all carbon atoms, this boron nitride comprises of like at sublattice A it is boron and sublattice B is nitrogen. And therefore, because of the sublattice symmetry breaking, it can create 6 eV gap. Now, the semiconductor component is this transition metal dichalcogenized, which is a new family recently played around like since 2010. So in this material, we have tungsten and sulfur.
And because of the subpolarity symmetry breaking between the two atoms, we have a gap of about 1 to 2 eV, which is perfect for transistors, just like silicon. Now this material, unlike these two are thin, one layer. This material, again, as I said, it is 3 atomic layers. We call this monolayer because like one unit cell, one monolayer. So this material is very interesting because it has 2 things that is uncommon. First, it has a new degree of freedom that we call a valley, which is also possessed in graphene. And secondly, it has a very large exciton binding energy because of the strong Coulomb interaction in this material. Now, so what does it mean by valley? Basically, if electrons are going through a lattice, it will experience scattering potential between the atoms. You go to this direction, that direction with different momentum wiggles. It will create energy landscape as a function of momentum, which sometimes can create a local minima, which you call a valley. Because once we excite electron hole carriers, these carriers can accumulate inside this valley, and therefore transport and optical properties of this material depend very much on the valley properties. So this material, because the structure is similar to graphene, it has a hexagonal Brillouin zone with 2 inequivalent values called the K and K prime points. It has a gap, and the valence bands are split by the spin-orbit coupling, where the spins are opposite in here. And if you go to the other valley, the spins are also opposite from the other valley. Now these conduction bands are empty, the valence bands are full. So for us, we are dealing light excitation or light control, then we only deal with the highest valence band and the lowest conduction band. Now, this material, again, has 2 interesting things. First, okay, we have 2 valleys, inequivalent valleys. Now, the unique thing is that this valley, you can excite electrons from the valence band to the conduction bands by using left circularly polarized light to do it at the K valley only. And if we switch our laser to the right circularly polarized light, we can do that at the K prime valley only. This is the selection rules, and if you'd like to know why, you can ask questions later. So secondly, it has a very strong excitonic binding energy, which means that this hole, which is positively charged, and these electrons, which is negatively charged, they are interacting through the attractive potential, Coulomb interaction, and it can create an excitonic state just below the band gap. And this is what usually happens for 3-dimensional semiconductors, but in 2-dimensional semiconductors, like this material, because it is so thin that the electric field that connects the hole and the electrons can escape outside the material, such that the electric field is no longer screened inside the material. So there are a lot of parts of the electric field that are clean, like not screened. Therefore, it is very strong and can form a tightly bound excitons. And therefore, the binding energy of the exciton is pretty large and pretty robust. You can see excitons at room temperature or even if you heat it up. So these are the 2 basic unique properties of this material. Now, okay. Now, these 2 values are energetically degenerate, and nothing will change this as long as the time reversal symmetry is preserved. But as we know, we can break time reversal symmetry by using magnetic field. In fact, there are a lot of people have done this, which shows that if we apply 10 Tesla of magnetic field, we can split the K and K prime valley valence band by about 2 milli-electron volts. For example, if we look up, excite the whole thing, and put electrons here, and you can wait until they recombine and emit photons. At 10 Tesla of magnetic field, this is the photoluminescence spectrum. Now, if you switch the magnetic field to negative 10 Tesla, then this is how the PL spectrum look like. So there's a shift, which is about 2 MeV at 10 Tesla. This is a very important measurement, but for practical purpose, it is still kind of like a small splitting. And then, since we'd like to study some non-equilibrium quantum matter as the title of our conference, then we want to know if we can use light to drive this system in order to achieve splitting to replace the magnetic field. So it turns out that we can, and we can do this by using the so-called optical Stark effect. Now, what is an optical Stark effect? Now, the physics of the optical Stark effect can be explained by a 2-level system. We have a ground state, we have excited state here, just like a ground state and exciton state in our material. Now, if this system is exposed to light below the gap, there is no net absorption. but there will be a coherent absorption that will create a photon rest state slightly below the gap. And because this photon rest state is very close to this excited state, it will repel each other. And similarly, if we can also create a state from the coherent emission to repel this state. Now, this results in gap that is slightly broadened by an amount of delta E. And so this is how we can shift the energy levels through the Floquet states, which is the photon rest states. But what are these photon rest states or Floquet states? And second question will be like, can we see these Floquet states? And is it possible to do this in a very selective manner? So then it comes to the second point that I will show you the Floquet states and how we can use this for Rayleigh splitting. Now, Gil, the previous speaker, has mentioned a lot about the Floquet states. So I'll just show you the picture. So we know that in condensed matter physics, we deal with crystalline solids, where the atoms are periodically arranged in space, like this. So there is a space periodic potential. Now, because of the space periodic potential, then we can have an energy dispersion that is periodic also in momentum, like space, momentum, they're canonical conjugate, so they can have periodicity. Now, this is called the Bloch states. And similarly, it turns out to be quite a general formulation that it also appears in the time periodic potential if we have a system that we drive with light, for example. Now, this time periodic potential will result in the energy dispersion that is also periodic in energy again. So, for example, this is without driving laser, but this is with a driving laser. So you can see that the energy band is duplicated up and duplicated down by an interval of h bar omega, which is the photon energy that we put, for example. Now, so let's just see this in experiments. So this is, for example, a bismuth selenide that has the Dirac cone. This is the Fermi level at 0 energy. So if we pump by using 0.1 electron volts of photon, then in principle we should be able to see the duplicated states, which is the Floquet states. And this is the movie taken by my colleagues Iwa Wang and also Fahad Mahmoud in the lab. And you can see once again, hopefully you can see that it is duplicated up and duplicated down, and it stops right there at 0 femtoseconds. Now, if we cut at the Fermi surface at 0 femtoseconds, we see initially it was just one circle, but it becomes like two circles because of the states coming from below. And if we look at the side cut, we can see and play again the time, then we can see that the states are actually duplicated, right? And then like start to filling all the higher bands. Now, this happens in the topological insulators, but of course we know that Floquet phenomena is kind of a general phenomenon, not only happens in topological insulators, but it was interesting in topological insulators because we can see that when we pump with light, the Floquet states, the Floquet sideband and the original state can overlap each other and can therefore split. Like as you can see that there is a splitting in here. But this is called the Floquet Bloch states. I'm not going too deep into this Floquet topological insulators, but I want to mention that it can also be seen in transition metal like chalcogenides. For example, this we can pump, we can see the original valence band can go up and can go down. Okay, so it is nice. So we go back to how we use the Floquet states in order to tune the energy levels. Now here is the optical Stark effect, and the gap that is changed because of the presence of the Floquet states can be seen as this formula, which is proportional to the dipole and electric field squared, which is the intensity of the laser pump, and inversely proportional to the energy detuning, which is the difference between the gap as well as the photon energy. Now, in our material, which is tungsten disulfide, we want to do this optical Stark effect. That means we have to pump the material. For example, this is the absorption spectrum of the exciton state that we are going to shift. So we pump below the exciton state, and then we expect a shift as simulated by this red curve. The shift is usually small, but it can be measured accurately by using the transient absorption spectroscopy, for example, in this experiment. So we have this material on the glass, and we pump with a strong laser, and we probe look at the reflectivity as we pump or as we block the pump, and we see the change of the absorption after and before pumping. So this is the experimental results, which shows that the change of the absorption after pumping is a differential curve, which means that consistent with the fact that the absorption spectrum moves to the higher energy. So this is it. And if we park our probe beam in here, we select one wavelength, and we change the time delay between the pump and probe, we see that the change of the absorption only happens at time 0 within the duration of the pulse width, which is about 160 femtoseconds. So this is the signature of the coherent interaction from the optical Stark effect. Well, this optical Stark effect is quite general. It has been seen in gallium arsenide semiconductors and many other semiconductors before. But what unique thing about this optical Stark effect is that it can be made valley selective, because the two valleys, the K and K prime valleys, obey different selection rules, or coupled differently with left and right cyclically polarized light. So if we pump this material by using left cyclically polarized light, we can see the optical Stark effect at the K valley. But if we switch to the K prime valley but keep the same pump polarization, we see nothing, or negligible. So that means the optical Stark effect is very contrast between the valley. Now, how do we understand this? We can understand this by a simple optical selection rules. So at the K valley, the valence band and the conduction bands have angular momentum quantum number, which is -12 and -3/2. This is, for example, given in the material system. So if we use left cyclically polarized light, which carries angular momentum of -1, then it will increase the quantum number to -3/2 for the photon rest state. Now, since the photon rest state and the conduction band have the same quantum numbers, so the matrix element provide a finite amount, and this will lead to the optical Stark shift. Now, at the K prime valley, the angular momentum are the opposite, and we still use same left cyclical polarized light, and the quantum numbers are not the same. Therefore, there is no optical Stark effect, but this will happen at the K prime valley if we switch the pump polarization, and this is what actually happens. So after switching the pump polarization to the right cyclically polarized light, the optical Stark effect can happen at the K prime valley. Okay, note that this is, we can say like this, there's an energy shift at the K prime valley, there's energy shift at the K valley, but we can also calculate how much the energy is shifted. Typically about like from 1 to 20 MeV, we can calculate by integrating the area under the curve, basically. So we do that with different laser fluence or intensity, and we can also change the laser color or changing the detuning. As an experimentalist, these are the two things that we can change easily for the laser experiments. So in this plot, we show the energy shift as a function of pump fluence measured at different laser pumping color or different detunings. So we can see when the detuning is very small, we can see the slope is higher, and the detuning is larger, we can see the slope is lower, but they are all follow linear slope. Now, if we have the same data and same energy scale, but the x-axis is changed to pump fluence over detuning, then we can see that all the data fall into the same slope, which means that this is exactly in excellent agreement with the optical Stark effect, which means that the energy shift is proportional to the light intensity of the pumping and inversely proportional to the detuning. So this is good. And nice thing is that we can shift the energy levels by about 18 MeV, which is large. And so with these experiments, I have shown that by using magnetic field and cyclically polarized light, we can split the two valleys because these two processes break time reversal symmetry. And note that we can generate 18 MeV of shift, which if we look at this, it corresponds to an effective magnetic field of about 90 Tesla, which we can usually only go there for to Florida or Tallahassee or in Europe also, national labs. Now this is nice. So far I've been discussing about the valley splitting optical Stark effect by using the small detuning. This is the regime where we put the photon energy slightly below the energy gap. But of course, we can also do similar things by using the so-called large detuning, where we have the energy gap and we only tune the photon energy about 1/3 of the gap, which is very far. So this is interesting because one of the things that it will show that something is breakdown, the James-Cummings model breakdown and so on. But okay, so we have been discussing about the Floquet states, the shifting of the energy levels through the optical Stark effect, and this is what happens, right? Ground state A, excited state B, we pump with light below the gap, and it will have this energy difference between the photon rest state and the gap, and this will increase the gap by this amount, E naught squared over E naught negative h bar omega. In fact, this is just one out of two in the general light matter interaction of the off resonance interaction. The other one, which is I call the abandoned twin, because I seldom hear it myself until I look at the data. Oh, this is very weird. But okay, it has a name called the Bloch-Siegert shift, which means that from the ground state, if we can absorb light higher, we can in principle emit the light down here. And then this is our new photon rest state, and the photon rest state would like to interact with the excited state still, but since the energy separation is much larger, the shift is also much smaller. And therefore, in many experiments, this is negligible. But since we tune our photon energy very low, though these two effects can be compatible, because the formula for this shift is similar, except that the denominator is actually the gap separation. This is plus and this is negative, right? Now, so what is interesting about the Bloch-Siegert shift? First is that there are three things. First, it has been seen exclusively in atoms. For the first time, the Bloch-Siegert shift is what actually the so-called lamp shift. It provides the shift to show that, oh, there is a quantum electrodynamics and mass renormalization in this hydrogen atom that Willis Lamb shown in his experiment that the shift corresponds to 4 micro electron volts, which is kind of small. But still, it is a very interesting case that he has observed. And then the Bloch-Siegert shift in atomic physics is usually mixed with the optical Stark shift. And if you want to use this for trapping the atoms, you have to calculate both the optical Stark shift as well as the Bloch-Siegert shift contribution. But in this talk, I want to show you that we can also observe this Bloch-Siegert shift in solids, as well as we can observe a large milli-electron volts, about 1,000 times larger. And then we can show that this optical Stark shift and Bloch-Siegert shift can be separated completely. So now, how do we do the experiments? So first, I want to recap what we've done in the optical Stark effect. Like before, we pump slightly below the gap, right? And we use left circularly polarized light, so the energy shift will happen at the K value and not at the K prime value. This we understand from the optical selection rules, right? Now, since as a graduate student we have a lot of time, so we want to do something else. Okay, how about we tune down here? Maybe like something interesting can happen, or prove our theory. Now, I did this, and then I went to the forbidden area. So we see a shift at the K value, and we also see a shift at the K prime value. Now, this happens after we increase the pump intensity by 10 times, of course, because we have lowered the energy so much. Okay, two things that we see to be explicit. First, we see some oscillations in here, right? And in here also. And second, yeah, as I said again, we see a signal at the K prime value. This, from the value selection rule, we shouldn't be able to see this. So that means that there is something that is weird. So I'm not going to touch about oscillations unless if you ask later on, but I will touch about the second point. Okay? So we want to understand this further. One thing that we can do is that we can calculate the energy shift by looking at the area under the curve. So we plot this shift as a function of fluence over the detuning. And for the K values, we can plot by using different laser colors. The solid symbols is at the K value, the open symbols at the K prime value. So the solid symbols all fall into the same line. So this means that this has a proportionality of 1 over the detuning, which is the optical Stark effect. But for the K prime values, all the open symbols, all the different colors of the pump photon energy all scattered into all different places. So this means that at the K prime value, the energy shift is not acting from the optical Stark effect. It must be something else. So what if we replot the same data, same y scaling, but change the x-axis into fluence over E naught plus h bar omega and plot the k prime symbols? And this is what happened. All the data points more or less fall into the same slope, and the slope has the same slope magnitude with this also. So that means like this has a proportional constant of 1 over E naught plus h bar omega, which is consistent with the Bloch-Siegert shift that I've shown you before. So we see something interesting. At the k value, we see optical shock effect. At the k prime value, we see the Bloch-Siegert shift. They are separated completely. And one thing is that we can see a Bloch-Siegert shift of about 10 milli-electron volts, which is pretty large compared to the atomic system, which was about 4 micro eV or something like that. Now, what is so special again? First, we see this in solids, and second, we see a large Bloch-Siegert shift, and third, it can be made separable. Now, how do we understand about this separability? We might understand about, okay, solids, okay, it should work in any system. Large, you can just crank up the intensity. But why is it separable? So we think further. So for the optical shock shift, it is the same explanation as before. Left circularly polarized light will create photon dry state with quantum numbers -3/2, and this is the same, they repel, but not at the k prime value. But for the Bloch-Siegert shift, instead of going up from the ground state, we can go down. So by emitting a sigma negative photon, by emitting a -1 angular momentum, it means we give +1 angular momentum to the new photon dry state. So from -12, it becomes +12, and these are different for the k value, but these are the same for the k prime value. Therefore, the Bloch-Siegert shift happens very exclusively at the k prime value, unlike the optical shock shift. Now, if you want to think further, then we can say that Bloch-Siegert shift is the counter-rotating wave term of the light matter interaction, and the optical shock shift is the rotating wave term of the light interaction. This is beyond the Jaynes-Cummings model in principle. Okay, now I'm going to talk about the Floquet topological insulators just like briefly. So yeah, there are many proposals, theoretical proposals by a lot of people in this audience. Nathaniel, Gil, Victor, Michael, Eugene. So basically the fact that if we have a trivial semiconductor or trivial gap insulator, then we can create a topological insulator out of it by driving the system with photon slightly above the gap. Then, for example, in this paper by Nathaniel, Gil, and Victor, they can create the Floquet bands in here, and this will repel each other, but it will create a metallic state in here in the middle of between the two bands. Now, similarly for graphene, you can also do the same thing, and by cranking up the intensity, you can create a like repulsion between the bands of the Floquet states, and then you can create, in principle, H state too, and many other proposals about this thing. Now, this is semiconductors, quantum wells, graphene. We can also, in principle, do the same thing with the TMDs, but we add a flavor called the Valley-Floquet topological insulator. Just combine all the terms. So this is still a proposal because it's difficult. So if we have a valence band, conduction band, and we pump with energy slightly above the gap, so it will create repulsion states at this point and at this point. And because the conduction band has a different characters, different quantum numbers, and different colors, so this metallic state should continue, the two of them, to preserve the topology. And so this is the so-called H state, metallic state. So there are some details about it, but I'd like to give you more description visually. So what happens is that if we have this material, we shine a circularly polarized light with this circular spot, then there exists a boundary, a one-dimensional boundary that separates a trivial insulator where it's normal gap and a non-trivial topological insulator where there is this gap in here. Now, this one-dimensional boundary hosts a one-dimensional electronic system where upspin electron will travel clockwise, and by switching the polarization, the downspin electron will travel counterclockwise. This is called the chiral H state, and this is very amazing because you can have an insulator in the middle, but you can have a metal on the outside. This is amazing because it looks like a burrito. So burrito is, we have in America, like this very peculiar, unique food that you cover all your food with a metal. And for those, because it's in Germany, so I'll just show you how the burrito looks like. So it's like this. So in summary, by using the transient absorption spectroscopy, we have shown the optical stark effect at the K value and also see beyond the James-Cummings model, which is the Bloch-Siegert shift. And there are several other things how Floquet states can be used to tune the energy levels. But I have not shown you here. For example, like we can combine two excitons to create bi-excitons. And this bi-exciton will have a state up here above the K and K prime value. And by pumping slightly above the gap, I was thinking to generate this chiral H states. But what I've seen is that I create a lot of excitons, and this bi-exciton state will also create Floquet states that will repel this energy level, and this will also repel energy level here, like a Zeeman-like system. And then we can also see a Lennard-Jones-like potential between two excitons because like two atoms. And if we look at a far distance, the two excitons will attract each other, and if it's too close, it will repel. Now, if I have more time, I would like to show like 5 minutes for the high harmonic arpex. Okay, see, maybe like 4.5 minutes. Okay, now why do we have this? Why do we have to make this high harmonic arpex? We can, in principle, go to synchrotron laboratory or by using laser arpex. But what is this high harmonic arpex? So we know in the transition metal like chalcogenides or any solids, we have a bunch of noodles, the band structures. And this is the gamma point in the middle, and then this is the K point. Our interest is to look at the K points. And if we have a brilliant zone like this, hexagonal for this material, by using 6 eV laser, we can do arpex at around the gamma point. But there's nothing interesting at the gamma point. The more interesting things happen at the K and K prime value, but we have to use a 30 eV laser. And then we can tilt the sample, and we can look at the K, M, K prime point of this material. Now, higher harmonics kind of like challenging, but we have to do that anyway. So this is our system that we've built. I started this thing like many years ago, and with the help of like many people, it can finally work out. So this is how we generate the UV light source, 30 eV photons, monochromator, diagnostic chamber to clean the XUV light, and the time of flight analyzer to see the arpex spectrum. And for example, in tungsten diselenide, we can see things at a gamma point, of course. And if we tilt the sample, we can see not only gamma point, but also K, M, K prime point, as we see the K and K prime values in the material. Now, how this is generated, basically we just use krypton gas, we drive with a strong intensity laser, and shake the potential well, and it generates XUV light. And you can see the jet of XUV light in here, which looks very purplish. Resolution is pretty good, and I show you just the last data I show you. So we want to see the valence band, the K and K prime point, and this is material looks like. So this is the results. We see K, K prime points, and we see from the theory it shows just one band. But of course, spin orbit coupling must be included, so there's a splitting. And not only that, we can see that this system can also generate or look at different momentum as you move from this line towards the gamma point. So you can see the structures is changing as you move to different momentum, and there is some splitting of the bands, and now they are going to go into forming the gamma point bands. So if we just like look at the snapshots like this, because of the good resolution of this system, then we can see like a very nice structures, like an eye or something like that. And if you go to Google and find random images, it may look something like this, like the social media. All right. All right. So I cannot show that too long. So basically, in summary, so by using laser arpex, we can generate the mapping band structure of the material. We can also see photon dry states. And with that, I'd like to thank the audience, also like my group leader, Professor GEDIK, as well as my collaborators, and also Liang Fu, our theory, Ishan, we got a sample from Ishan and Jing Gong also, and as well as the theory for the Floquet by Victor and also Benjamin, and also to thanks Martin Zurlein about discussing about the Bloch-Siegert shift. And with that, thank you so much, and yeah.